So welcome back. We in the last lecture saw some puzzles. The game with the marble, back solitaire, 15 puzzle, and now we are moving on to Rubik's cube. And to understand Rubik's cube, there are a few more things that one has to understand. How to solve Rubik's cube using ideas of mathematics, ideas of group theory. Because Rubik's cube, as I said, is playing Rubik's cube is just permuting certain small cubes, right? So everything now is about generators and relations. So what are generators, what are relations, and how you can present, how can you express a group as generators and relations. That's what we are going to learn. So for that, we begin with an example, and you have already seen this example in one of the earlier lectures, and this example is about symmetries of a square. And as I said during previous lectures, that they form a group. The group is called D4. 4 stands for 4 sides of a square. So let's see what are all the symmetries of a square. I take this as identity position 1, 2, 3, 4. That is identity position. R stands for rotation by 90 degree in anti-clockwise direction, and F stands here for flipping about x-axis. So accordingly, I am going to label all these configurations, configurations of a square. So when I rotate by 90 degree, what happens to 2? 2 goes to this position. 2 comes here. What happens to 1? 1 comes here. What happens to 4? 4 goes there. And 3 comes here. So we have like this. Once again, I rotate this configuration by 90 degree, and what do I have? 1 comes here this time, this side. So I have 1, 2, 3, 4, and once more. This time 1 goes here, and I have 1, 2, 3, 4. So there are 4 positions. So first 1 is here, then 1 is here, then 1 is here, then 1 is here. Similarly, you have other configurations. Now what happens when you flip about x-axis? So that's the x-axis I am flipping. So 1 comes here, 2 comes here, 4 comes here, and 3 comes here. And after flipping, I am again doing what I did earlier. I rotate by 90 degree. So this time 1 goes here. So I have 1, 2, 3, 4. Once again 1, 2, 3, 4, and once more. So this time I have 1 here, 1, 2, 3, 4. So here I have obtained all these configurations of the square. Just have to check that these are all 8 possibilities. There are no other. There are no other possibilities. So this I denote by identity 1, this I denote by R, this I denote by r square, this I denote by r cube. What about this one? Here I do first f, so this is f, so this is what? This is, I first do f and then r, f r square, f r cube. So like that I have various configurations. What about flipping about y-axis? Have I already covered it? Let's see, this is the original position, this is the original position, and flipping about y-axis will be 2 here, 1 here, 3 here, 4 here. So 2 here, 1 here, 3 here, 4 here. It is this one. So this is actually, we want Fy. This is Fy, flipping about y-axis. Similarly, I have also covered flipping about diagonal somewhere. So that's interesting, right? I did flipping only about x-axis, and by composing it with rotations by 90 degree, I could cover flipping about y-axis as well. Similarly, I have also covered flipping about the diagonal. Let's see how. So suppose you take this diagonal 1, 3, and about this diagonal, so that means 1, 3 will remain here, 2 will come this side and 4 will go that side. So 1, 3, 1, 3, 2, 4. So this is actually flipping about diagonal 1, 3. So in fact all the possibilities have been covered. So that's interesting. What does it mean? That means to obtain Fy, what you need is f and r and r. You first have f, then r, then r. And similarly, to flip about diagonal, what you need is first flip about x-axis. So f is fx. Flip about x-axis, then r, then r, then r. So in that sense, you can obtain Fy from r and f. In fact, all these 8 elements are generated by just 2 elements, f and r. Rotation by 90 degree in anti-clockwise direction and flipping about x-axis. And that's how we start calling f and r as generators for the group D4. So I have r, I have f. So these are 2 generators. Just by combining them in certain fashions, I can obtain everything in this group. And what are the relations? Relations are, if I do r 4 times, I rotate by 90 degree 4 times. I get back my identity, and if I flip about x-axis twice, I get back my identity, and then there is some relation between fr and rf. Let's see what kind of relation it is. So I have written r square f. What about fr? So let me try to write fr here. So you have this square, I have 1, 2, 3, 4. So after f, what will happen? No, this is this is Control Z. So you have fr here. So first I'll write what r is doing. R is doing it 2, 3, 1, 4. That is r, you see. And then I am doing f. What is that? Flipping about x-axis. So 1, 4 here and 2, 3 here. So where is 1, 4, 3, 2? So it's 1, 4, 3, 2. So fr is actually this one. Fr is actually equal to r cube f. So these are relations. So fr is same as r cube f. So you have this RF, and conditions are these. So notation goes like this. So this is what? This is group generated by R and F with relations as expressed here. So every group can be expressed in terms of the generating set and relations. Generating set need not be unique. In fact, in place of taking this fx, I could have taken say fy, and then the same group would have got generated with those generators. So I could have used some other set of generators. So these are generators and these are relations. Generators. Similarly, you can try to think about other generators, other relations in some other groups. So if I take the general situation Dn, what was Dn? Dn is symmetries of regular n-gon. Then the relations would be essentially similar except for so Rf, where r to the power n is 1, f square is 1, and then frf is r to the power n minus 1. So these are the relations there. In general, it's very difficult to determine from generators and relations what exactly is the structure of the group, what exactly does the group look like. The same group can be expressed by a different set of generators and different set of relations. That's quite possible. So in general, it's a very difficult problem to make a guess about what the group is going to be just by looking at generators and relations. Nevertheless, it's quite important in mathematics to understand, it's quite important in theory of groups to understand what are relations in a group, and it's always desirable to find the maximal set of relations. Let's take few more examples. The easiest example actually now. What about Z? So if I take some element in Z, say I take 3. If I take this element 3, so I can ask the group, or rather the subgroup of Z, which is generated by 3. So if 3 is there, 3 plus 3, 6 has to be there, 9 has to be there, and so on. Of course, in the group 0 has to be there. If 3 is there, minus 3 has to be there. Since 6 is there, minus 6 has to be there, like that. So subgroup of Z which is generated by 3 eventually turns out to be, these are multiples of 3, integral multiples of 3. These are integral multiples of 3. So 3Z, integral multiples of 3, that is just subset of Z. But if I take 1, so if I take 1 and the group generated by 1. So for any subset S in Z, this is group generated. What's the meaning of group generated? The smallest group which contains S. So this is smallest subgroup of Z that contains S. So if I take 1, then it is equal to Z. So 1 is a generating set of Z. However, I could have taken S to be say 2 and 3. See, if 2 is there, 4 has to be there, 6 has to be there and all that, 0 has to be there, minus 2 has to be there and like that. And since 3 is there, all multiples of 3, 3, 6, 9, all of them have to be there as I said. But then since 2 is there and 3 is there, the difference of them also has to be there. So 1 also has to be there in the subgroup generated by S. And since 1 is there in the subgroup generated by S, the subgroup generated by S is actually Z. So there are various generating sets for Z. So Z is generated by say 1, Z is generated by say 2, 3, or you take any co-prime integers n and m, co-prime, then in fact they are going to generate Z as a group. So there is no uniqueness in the set of generators of a group. Now think of this, Z as generated by 1. So Z as generated by 1. Where are the relations? What are the relations? So since 1 is here, 1 plus 1 is here, 1 plus 1 plus 1 is there and so on, and 0 has to be there as I said, minus 1, minus of 1 plus 1 and so on. There are no relations in Z. And just a way to say it is, you take any symbol A. So in the group which is generated by A square is there, A cube is there and so on, identity element is there, A inverse is there, A to the power minus 2 is there, A to the power minus 3 is there and so on. So there are no generators, there are no relations. Generator is of course singleton A, but there are no relations. So Z is therefore called free group on one symbol or one letter. So when we don't enforce any relations, what you have is free group. Free group has much more abstract definition, which is in terms of certain universal property, but in these lectures we are not going to be bothered about that definition. So let's understand free groups. So what I have is to start with free groups on two letters. So those two letters are A and B, just two symbols. So any combination of A and B has to be there in the free group, and then there are no relations. So how do we go about? A is there, B is there. I introduce two more symbols, A prime and B prime. And then I consider with these 3-4 symbols, with these 4 letters, I make words. So how do words look like? Any sequence of them, any sequence of A, B, A prime, B prime, and in any fashion, of any length. So say A, B, A prime, B, A. That's one. A prime, B prime, A prime, A, B. That is one. A prime, B prime, B. That is one. A prime. That is one. So there are so many words which are there. So what am I doing? With these 3-4 letters, I am constructing actually all possible words of all possible lengths. So I am having dictionary of these words. So I am constructing a dictionary out of all these words. So words of all lengths. And here I would be slightly careful because I have to talk about groups. So group relations, the group axiom should be satisfied, and it should be clear why A prime and B prime were introduced. So what I would say that whenever A and A prime occur in the word back to back, or B and B prime occur in a word back to back, then I'll just collapse them, and then I would say that after collapsing that this is A prime, B prime, B. So this word is actually equivalent to this word. It's equivalent to this word. And again B prime, B are coming together, they'll collapse, and then this is equivalent to A prime. Okay. So I am considering words of all length, and I am just being careful that I am identifying equivalent words. Okay. So what do I have now? I have I started with just two letters, A and B. I put two more words, two more letters, A prime, B prime, and A prime was introduced so that A prime can act as inverse of A, and B prime was introduced because we wanted something to act as inverse of B. And keeping that spirit, we created the definition of equivalent, so that whenever B prime B and B prime come together, or A and A prime come together, I collapse it. So just from two letters I can create huge collection. Okay. So I have all this dictionary. So from A prime B, so from AB I have AB, A prime, B prime, and then I have all words up to equivalence, meaning the two equivalent words. There were two words which are equivalent, I am going to treat them same. So this collection is called F or FAB, which is free group on AB. How big is this group? It's huge. It's infinite group. It's really huge. And how do I take group operation in this group? I just take a word, say A prime, B, A, and here I have some word A, B, A, B prime, some word. So what's the composition? What's the group law on them? Juxtaposition. You just place these two words back to back. Place one first word, then you place second word, just merge it in the formal fashion. So what is that? A prime, B A, A B, A B prime, right? A prime B A and A B prime. So simplified form of this would be just a notation A prime B. When you have A and A back to back, its notation is A square, and then B A B prime. If there were some other word, say if there was A B prime here, and if B prime B were here, well B prime B is identity, maybe B prime B A were here, then what would I do? I would just simply consider the composition of them as A, B prime, B prime, B A. So I would just dissolve it. I would just say B prime B is identity. So this would be just A, B prime, A, right? So whenever you have A and A prime or B and B prime, you're just going to collapse it. So this is how free groups work. One query that you may have is, what are they good for? Their construction looks so abstract, just having two symbols, two letters, and from those two letters you are constructing a huge group. What's the advantage of having such definitions? Maybe it's used for abstract mathematics. Is there an application of this beyond it, beyond this construction? When we discuss Rubik's Cube, I would show you how useful is the concept of free groups. Few more words before I stop. Here is a notion of quotienting, which I am not going to make very precise. So whenever you have a group G and whenever you are having a subgroup H, is a definition. It's normal subgroup. So this setup H subgroup of G you would call normal subgroup if you pick any element of G and any element of H and you consider G H G inverse. This is so called conjugation. You are conjugating H by G, then that should also belong to G. Sorry, that should belong to H. So if H has this property, then we call it normal subgroup, and the notation is H is normal subgroup of G. And whenever you have normal subgroup, to this you associate another group which is G mod H. This is notation. It's called quotient of G by H. So we are having some quotienting of G by H. I'm not going to define it, but some words I am saying, so one can think of, as the time comes, maybe I would explain it in detail. If you have any group G, then I can express G as a quotient of free group by some subgroup, some normal subgroup of free group. So normal subgroups are going to arise naturally when we learn homomorphisms, isomorphisms. In previous lectures, I just briefly mentioned the word homomorphism and isomorphism, but normal subgroups are going to arise when we talk of kernels of homomorphisms. So when we discuss Rubik's cubes, kernels of homomorphisms are going to play an important role. So we should see all that in the next lecture. Keep watching. I hope you are enjoying all this. Thank you.